Okay, awesome. I think we're ready to move on to 7-2. Do you remember what an integral is?
Yeah, that's uh, uh, uh,
Two hours later.
I remember now. Yes, it's the function of which a given function is a derivative, i.e., which yields that function when differentiated, and which may express the area under the curve of the graph of the function.
Yeah, that's exactly what the definition is. All right. Now we're finally ready to start 7-2.
Awesome!
So if the integral is the area underneath one curve, what about the area between two curves?
Great question. Let's find out. Here's the definition. If we have a function f of x and a function g of x, where f of x is greater than g of x, you should subtract the functions and define your integral with this new equation on your desired interval, a to b.
Awesome. Alright, so can you show me an example of that?
Sure, take a look at example 1. So the first thing you want to do is find which function is higher than the other.
Alright, so that would be secant squared of x.
Right. So then you want to take the two functions, subtract the lower one from the higher one, and then that's your new equation that you can solve. Alright, so you start by subtracting sine of x from secant squared of x. Then, you integrate them, and they give you limits in the problem, so it's from 0 to pi over 4. Now the integral of secant squared of x is tangent x, and the integral of negative sine of x is positive cosine of x. Then you plug in pi over 4 and 0, and your answer should be radical 2 over 2 units squared.
Alright, so you showed me an example where we found the area between two curves that didn't touch. What about the area of an enclosed region where the graphs overlap?
Well, let me show you. The first step is finding the limits of integration. So the first step of solving problems where you need to find your limits of integration is setting your two equations equal to each other. In this case, we set 2 minus x squared equal to negative x. We solved for x and got x equals 2 and x equals negative 1. Those two numbers are your new limits of integration. Then, the problem becomes just like example 1. You subtract the lower function from the higher function, you solve with respect to your limits of integration, and your final answer should be 9 over 2 units squared.
Nice!
Okay, so do you think you're starting to understand how this works?
Yeah.
Awesome. So this next one requires a calculator. I think I'll let you try it on your own.
Nice. I'm a calculator whiz. So I'll start off by graphing these two graphs. 2 cosine of x, and underneath we're going to put x squared minus 1. So as you can see, these graphs intersect, and they create an area between, right? So now I'm just going to put my handy dandy mouse right over the intersection, and it should give me the point. So there you go. The x values at which they intersect are negative 1.265 and positive 1.265. Here I have already predetermined what I'm going to graph. I'm just going to show you guys how to graph this really quick on the TI-89 that we all have. So we're going to go to graph, and we're going to find out what that looks like. So there you go. So now also on the TI-89, we can go over here to F5. We can find the intersection between our two graphs by simply finding the limits on our first curve and on our second curve, finding the lower bound, and finding the upper bound. So now we see our intersection is at negative 1.265. Now, since I know that these graphs are both symmetrical, on the other side, on the positive side, there's going to be a 1.265 intersection there as well. So now that we know that, let's go over to integrate. So what we're going to do now is F3, we're going to integrate, and we're going to use our original functions, 2 cosine of x minus x squared minus 1. So minus x squared plus 1. With respect to x, from negative 1.265 to positive 1.265. Close parentheses, and we should get our answer.
Hey, awesome job with example 3.
Yeah, I'm really feeling this now. I could do example 4.
Alright, you know what? I'm feeling this so much. I feel like I could bring it into the third dimension. Let's bring it out here.
Alright, so this graph looks kind of weird. So the first thing we're going to do is we're going to graph them out, and we're going to look at the image a little bit. So let's divide it into two parts, A and B. A is bounded, as you can see, by the x-axis, from 0 to 2. B is bounded, however, by the line x minus 2, from 2 to 4. So since there's two different segments, we're going to have to need two different integrals. Once we define these integrals, we're just going to have to add them together and solve normally. Since root x is only bounded by the x-axis from 0 to 2, we're just going to take it normally and find the integral for that. However, with b, we're going to use the concept we previously learned, and we're going to take the top and subtract it from the bottom. So we're going to take root x, and we're going to subtract the function x minus 2. So now we just think back that a total is the sum of its parts. So we're just going to add a and b, or the integrals that we defined for them, and we're going to solve it out and get 10 over 3 units squared.
Nice! Hey, awesome job with example 4. Example 5 is a little tricky though. We're going to need the help of some technology. Follow me.
Wait. Respect to y? But why?
Don't worry, it's not as hard as it looks. In this situation, you're going to want to rewrite your equations so you isolate your x. Therefore, your equations will be in terms of y. So where you'd have an f of x, you now have an f of y, or a g of y. Then you want to find your new limits in terms of y. As you can see, d and c represent your new limits. So where you'd normally look at your limits from left to right, you're now looking from down to up. Therefore, the lower number is your lower limit. So c would be your lower limit, and d would be your upper limit. Your new greater function would be the function that's farthest to the right, because it has the largest x values rather than the largest y values. Then it becomes as easy as solving examples 1 through 4.
Whoa. Slow down there, Speedy Gonzalez. I'm still not getting this.
You know what? It'd just be easier if I showed you an example. Alright, so remember example 4?
Yeah, I kind of just did it.
Alright, well we're gonna do it again. So when integrating with respect to y, you want to rewrite your equations in terms of y. So y equals x minus 2 becomes x equals y plus 2, and y equals radical x becomes x equals y squared. Then you can write your integral. So your limits are 0 and 2, and you write y plus 2 minus y squared. Remember to do this with respect to y. Then you solve your integral, and your final answer should be 10 over 3 units squared.
Oh, okay. I think I'm starting to get it a little bit. But let's say we have an occasion where we can use either or. Which one do I use?
Well, that's where you have to make the choice. As you can see here, we have our functions typed in, all in terms of x. So the original function, y equals x cubed is still there, but the function x equals y squared minus 2 would get changed to positive radical x plus 2 and negative radical x plus 2. Then we would graph these. Okay, so here's our graph. As you can see, it has 2 points of intersection here and here. Now, if we were to do this in terms of x, you would see that the leftmost point of intersection is not the leftmost point of the area. We'd be able to integrate it in terms of x from this point to the rightmost point, but this area over here would not be accounted for, which is why this problem is more useful to be integrated with respect to y. Okay, so to solve this function, we're going to have to write our equations in terms of y. So the first equation is given to us in terms of y. It's x equals y squared minus 2. And then the second equation is y equals x cubed. But we can solve that in terms of y just by rewriting it. So we get x equals y to the 1/3 power. So now we need to find our new points of intersection, which is easy. We go back to the solve function, and then we type both of our equations, y squared minus 2, set it equal to y to the 1/3 with respect to y, and that should give us 2 points. So those are our 2 points, y equals -1 and y equals 1.79. So then, with these 2 points, we can now integrate. So we go to f3 and 2. We write our higher function, or in this case the function that's furthest to the right, which is y to the 1/3. And then subtract y squared minus 2, so minus y squared plus 2. Make sure it's with respect to y. And then you want to put your lower limit, which is negative 1, and your upper limit, which is 1.793. And then you can solve. And there's your answer, 4.215. Okay, and that's pretty much how you do examples.
You know what? I really like using shapes.
Oh. Well, lucky for you, I have just the example.
Oh, it's beautiful, yet familiar. Alright, so when using geometry, we're going to first graph the functions. We're going to use f of x, which is the square root of x, and we're going to use g of x, which is x minus 2. But let's see. When we form the graph, what do we form? Rectangles! No, Patrick. That's a triangle. So the first thing we're going to do is we're going to take the square root of x and integrate it all the way from 0 to 4. Now, if you notice, this is the whole entire domain of the graph that we're looking at. But what we're going to do is we're going to subtract the triangle area. So we're going to solve for the integration, and we're going to subtract the 1/2 base times height. Base of the triangle being 2 and the height also being 2. So we get 16 over 3 for the integration, and we get 2 for the area of the triangle. So when we subtract both, we get our familiar answer of 10 over 3 units squared.
Okay, and that's basically all the lesson.
I get it now, and so can you.